The Milky Way galaxy is one of the most fascinating and complex structures in the universe, a vast cosmic entity that serves as the home to our solar system and countless other stars, planets, and celestial phenomena. It is a barred spiral galaxy, a classification that denotes its unique structure, marked by a central bar-like formation from which its spiral arms extend. The Milky Way's sheer size, estimated to be around 100,000 light-years in diameter, encompasses an extraordinary diversity of stars, star clusters, gas clouds, and other forms of matter, all bound together by the force of gravity. Understanding the Milky Way is not just about appreciating the beauty of the night sky but also about delving into the fundamental processes that govern the evolution of galaxies and the universe itself. The name Milky Way originates from its appearance as a milky band of light stretching across the night sky, a phenomenon that has inspired myths and legends across various cultures for centuries. This diffuse glow, visible on clear, dark nights, is produced by the light of billions of stars that are too faint to be resolved individually by the naked eye. These stars are located in the dense central region of our galaxy and its spiral arms, which are rich with stellar populations. It wasn't until the invention of the telescope and subsequent advancements in astronomy that scientists began to understand the true nature of the Milky Way as a galaxy, a massive, gravitationally bound system of stars, stellar remnants, interstellar gas, dust, and dark matter. The Milky Way is classified as a barred spiral galaxy, a subtype of spiral galaxies that includes a prominent elongated bar structure of stars extending from the central bulge. This bar is thought to be composed of older, reddish stars and spans a significant portion of the galaxy's width. The presence of the bar influences the dynamics of the galaxy, driving the flow of gas and stars within the galactic disk. This bar structure channels gas from the outer regions towards the center, fueling star formation and feeding the supermassive black hole known as Sagittarius A, that resides at the core of our galaxy. The spiral arms, which emanate from the ends of this bar, are sites of active star formation and are rich with younger, hotter, and more massive stars, as well as giant molecular clouds that serve as stellar nurseries. The structure of the Milky Way is not a simple, uniform disk, it is a complex, multi-layered system consisting of several distinct components. At its heart lies the galactic bulge, a densely packed region of stars, gas, and dust that forms a spherical or elliptical shape around the galaxy's core. The bulge is primarily composed of older stars, including a significant number of red giants, and it is thought to have formed early in the history of the Milky Way. The stars in this region follow more chaotic orbits compared to those in the galactic disk, where most stars, including our Sun, are found. Surrounding the bulge is the galactic disk, a flattened structure that extends outward, containing the spiral arms. This disk is where the majority of the Milky Way's star formation occurs, and it is rich with interstellar material, including vast clouds of gas and dust that provide the raw ingredients for new stars. Beyond the disk lies the galactic halo, an expansive, roughly spherical region that envelopes the entire galaxy. The halo contains some of the oldest stars in the Milky Way, often found in globular clusters, tightly bound groups of tens of thousands to millions of stars. These ancient stars are believed to be remnants from the early stages of the galaxy's formation. The halo also contains a significant amount of dark matter, an enigmatic substance that does not emit or absorb light but exerts gravitational forces. Dark matter plays a crucial role in the galaxy's overall structure and dynamics, helping to hold the Milky Way together and influencing the motion of stars, especially those in the outer regions. The Milky Way's mass is another area of great interest to astronomers. Current estimates suggest that the galaxy contains between 100 billion to 400 billion stars, along with vast quantities of gas, dust, and dark matter. The total mass of the Milky Way is thought to be around 1 trillion times that of our Sun. This mass is distributed across its various components, with the dark matter halo accounting for the majority. The gravitational pull of this immense mass keeps the galaxy's stars and other objects in orbit around the center, much like the way the Sun's gravity holds the planets of our solar system in their orbits. The mass distribution within the Milky Way also affects its rotation curve, which does not decline with distance from the center as would be expected if only visible matter were present. Instead, the rotation speed remains relatively constant, a phenomenon that provided early evidence for the existence of dark matter. The Milky Way is not an isolated system, it is part of a larger cosmic neighborhood known as the Local Group. This collection of more than 50 galaxies includes both large spiral galaxies, like the Milky Way and Andromeda, as well as numerous smaller dwarf galaxies. The Local Group itself is part of an even larger structure called the Virgo supercluster, which contains thousands of galaxies bound together by gravity. These structures highlight the hierarchical nature of the universe, where galaxies form clusters, superclusters, and cosmic filaments that stretch across billions of light years. The Milky Way and Andromeda are the dominant members of the Local Group, and their gravitational interaction is expected to culminate in a cosmic collision, and merge billions of years from now, eventually forming a new galaxy. The study of the Milky Way's structure, composition, and dynamics has been greatly advanced by modern observational techniques and instruments. Radio telescopes, infrared observatories, and space missions like the Hubble Space Telescope and the Gaia satellite have provided unprecedented insights into the galaxy's properties. For example, Gaia's mission to map the positions and motions of over 1 billion stars in the Milky Way has led to the most detailed three-dimensional map of our galaxy ever created. This data helps astronomers understand not only the current structure of the Milky Way but also its history, including how it formed and evolved over billions of years. One of the key challenges in studying the Milky Way is our location within it. As we are situated on the inner edge of one of the spiral arms, our view of the galaxy is obstructed by dense clouds of gas and dust, particularly in the plane of the galactic disk. This makes it difficult to observe certain regions, especially those near the galactic center. However, by using observations in different wavelengths, such as radio and infrared, which can penetrate dust clouds, astronomers have been able to uncover much about the hidden structure of the Milky Way. For instance, radio waves allow us to trace the distribution of neutral hydrogen gas, revealing the spiral arm structure and mapping the galaxy's large-scale dynamics. The discovery of the Milky Way's spiral structure dates back to the mid-20th century when astronomers first began to map the distribution of gas clouds in the galaxy. Using radio observations, they were able to identify several spiral arms, each named after the constellations in which they are most prominently seen, such as the Perseus Arm and the Sagittarius Arm. These arms are not rigid structures, rather, they are areas of higher density where stars, gas, and dust are more concentrated. The spiral arms are believed to be formed by density waves, regions of increased gravitational pull that move through the galactic disk, compressing gas and triggering star formation as they pass. This wave-like motion helps maintain the spiral pattern, despite the differential rotation of the galaxy where stars closer to the center orbit faster than those further out. The study of the Milky Way's bar structure has revealed that it is an essential component of its dynamics. Observations suggest that the bar rotates, sweeping gas and stars along with it, and potentially influencing the formation of spiral arms. The exact mechanisms behind the formation of the bar are still not fully understood, but it is thought to play a role in the redistribution of angular momentum within the galaxy. This redistribution can affect the orbits of stars, leading to the migration of stellar populations across the galactic disk. Understanding the bar's influence on the Milky Way is crucial for developing accurate models of galactic evolution. The central bulge of the Milky Way is another region of intense study. The bulge is home to a dense population of stars, many of which are older than those found in the disk. It is also the location of the supermassive black hole, Sagittarius A, which has a mass of about 4 million times that of the Sun. The discovery of this black hole was a significant milestone in astrophysics, achieved through observations of the orbits of stars near the galactic center. These stars exhibit high velocities, indicating the presence of a massive, compact object exerting a strong gravitational pull. The study of Sagittarius A provides a unique opportunity to understand the nature of supermassive black holes and their role in the formation and evolution of galaxies. The Milky Way's relationship with its neighboring galaxies, particularly those within the local group, is a dynamic one. The gravitational forces between these galaxies result in interactions that can lead to the exchange of stars and gas, as well as tidal disruptions that shape their structures. For example, the Milky Way is currently absorbing smaller satellite galaxies, such as the Sagittarius dwarf galaxy, which is being torn apart by tidal forces as it orbits our galaxy. These interactions contribute to the Milky Way's growth and help astronomers understand the processes of galactic cannibalism and hierarchical galaxy formation. The local group itself is part of a larger, more complex network of galaxies. The Milky Way's place within the Virgo supercluster and the even more extensive Laniakea supercluster illustrates the interconnectedness of galaxies on a cosmic scale. These large-scale structures are shaped by the gravitational influence of dark matter, which acts as a framework around which galaxies and clusters coalesce. Understanding the Milky Way's position within these larger cosmic structures provides insight into the processes that govern the formation of the universe on the grandest scales. The Milky Way galaxy is not just our cosmic home but a complex, dynamic system that offers a microcosm of the processes that govern the universe. From its intricate spiral structure and star-forming regions to its ancient halo and central supermassive black hole, the Milky Way serves as a laboratory for understanding the life cycles of stars, the distribution of dark matter, and the evolution of galaxies. Its interactions with neighboring galaxies and its role within the larger cosmic web underscore the interconnectedness of the universe. As observational technology continues to advance, our understanding of the Milky Way and its mysteries will only deepen, offering new insights into the origins and fate of galaxies and the universe itself. The Milky Way galaxy, a barred spiral galaxy, is a vast and complex system that stretches approximately 100,000 light-years in diameter and contains hundreds of billions of stars, as well as a diverse array of interstellar matter. Its structure is composed of multiple distinct regions, each with its own unique characteristics and significance in the overall dynamics and evolution of the galaxy. These regions include the central bulge, the galactic disk with its prominent spiral arms, the surrounding halo, and the pervasive presence of dark matter that influences the galaxy's structure. Understanding the composition and structure of the Milky Way is crucial for unraveling the mysteries of galaxy formation, star formation, and the cosmic processes that shape the universe. At the heart of the Milky Way lies the central bulge, a densely packed, roughly spherical region of stars, gas, and dust. The bulge extends outwards for about 5,000 light-years from the galactic center and is predominantly composed of older stars, many of which are red giants and variable stars. This dense stellar population is thought to have formed during the early stages of the galaxy's evolution, possibly as a result of rapid star formation and merging events. The stars in the bulge have diverse orbits, unlike the more orderly rotation of stars in the galactic disk, indicating a chaotic formation history. Within the central bulge, at its very core, resides a supermassive black hole known as Sagittarius A, pronounced Sagittarius A star. Sagittarius A is one of the most intriguing features of the Milky Way's central region. This supermassive black hole is estimated to have a mass of about 4 million times that of our Sun. The discovery of Sagittarius A was a significant breakthrough in astrophysics, primarily achieved through radio observations and tracking the orbits of stars near the galactic center. Astronomers noticed that stars close to this region exhibited rapid and highly elliptical orbits, indicating the presence of a massive, invisible object exerting a strong gravitational pull. This led to the conclusion that a supermassive black hole was the only plausible explanation for the observed stellar dynamics. The study of Sagittarius A continues to be a focal point in understanding the behavior of black holes, as well as their impact on their surrounding environments. Although Sagittarius A itself is relatively quiescent compared to more active galactic nuclei in other galaxies, it occasionally emits flares, likely due to the accretion of matter falling into the black hole. Surrounding the central bulge is the galactic disk, a vast, flattened structure where the majority of the Milky Way's stars, gas, and dust are found. The disk extends outward to a radius of about 50,000 light-years, and is the site of the galaxy's most prominent features, the spiral arms. These arms, which are regions of enhanced density, are not solid structures but rather areas where stars, gas, and dust are more densely packed than in the inter-arm regions. The Milky Way has several named spiral arms, such as the Perseus arm, the Sagittarius arm, and the Scutum Centaurus arm. These arms are home to active star-forming regions, where clouds of gas collapse under gravity to form new stars. The spiral arms are delineated by the presence of hot, young, blue stars that emit large amounts of ultraviolet light, making these regions some of the brightest in the galaxy. The formation of spiral arms is believed to be driven by a phenomenon known as density wave theory. According to this theory, the spiral arms are created by waves of higher density that travel through the disk of the galaxy. These density waves act like traffic jams, slowing down the movement of stars and gas as they pass through, which leads to the compression of gas clouds and triggers star formation. This process is somewhat analogous to the way a moving crowd of people might slow down and bunch together when passing through a narrow doorway. The stars and gas in the spiral arms are constantly moving in and out of these regions of higher density, which means that the arms are not composed of the same stars over time but are instead dynamic features of the galactic disk. This dynamic nature of the spiral arms plays a crucial role in the ongoing process of star formation and the overall evolution of the galaxy. The galactic disk is also divided into two main components, the thin disk and the thick disk. The thin disk contains most of the Milky Way's young stars, open star clusters, gas, and dust, and it is where active star formation is most prevalent. The thick disk, on the other hand, is populated by older stars and is less rich in interstellar material. These two components differ not only in their stellar populations but also in their scale heights and metallicity distributions. The existence of the thick disk suggests that it may have formed through different mechanisms, such as early mergers with satellite galaxies or the heating of the thin disk by interactions with dark matter substructures. Beyond the galactic disk lies the galactic halo, a roughly spherical region that envelops the entire galaxy. The halo extends well beyond the visible parts of the Milky Way, reaching distances of up to several 100,000 light-years from the galactic center. This halo is sparsely populated with stars, many of which are found in globular clusters, dense, spherical collections of stars that are among the oldest known objects in the galaxy. The stars in the halo are typically older, metal-poor, and have orbits that are more elliptical and randomly oriented compared to the stars in the disk. The halo also contains a significant amount of dark matter, an invisible and mysterious substance that does not emit or absorb light but exerts a gravitational influence on visible matter. The presence of dark matter in the galactic halo was inferred from observations of the rotational speeds of stars in the outer regions of the Milky Way. According to Newtonian mechanics, one would expect the rotational velocity of stars to decrease with distance from the galactic center, similar to the way the outer planets in our solar system move more slowly than those closer to the Sun. However, astronomers have found that the rotational speeds of stars in the Milky Way remain relatively constant, even far from the galactic center. This flat rotation curve suggests that there is a substantial amount of unseen mass in the halo providing the necessary gravitational pull to keep the stars moving at such high speeds. This unseen mass is attributed to dark matter, which is thought to make up about 85% of the total mass of the Milky Way. The exact nature of dark matter remains one of the most profound mysteries in astrophysics. Various candidates have been proposed, ranging from exotic particles like WIMPs, weakly interacting massive particles, to more familiar but hard-to-detect objects like MACHOs, massive compact halo objects. Despite extensive efforts, dark matter has so far evaded direct detection, but its gravitational effects on galaxies and clusters are well documented. The study of dark matter is crucial for understanding not only the Milky Way but also the formation and evolution of galaxies throughout the universe. In addition to stars and dark matter, the Milky Way is rich in interstellar gas and dust, which play a fundamental role in the cycle of star formation and the chemical enrichment of the galaxy. The gas in the Milky Way is predominantly composed of hydrogen and helium, with traces of heavier elements. This gas is distributed throughout the galactic disk, particularly within the spiral arms where it is most concentrated. Interstellar dust, which is made up of tiny solid particles of carbon, silicon, and other elements, is mixed with this gas and can absorb and scatter light, creating dark nebulae that obscure our view of certain parts of the galaxy. The interstellar medium, which includes both gas and dust, is the birthplace of stars. In regions known as molecular clouds, the gas and dust are dense and cold enough for molecules to form, particularly molecular hydrogen, H2. These molecular clouds are often referred to as stellar nurseries because they are the sites where new stars are born. The process of star formation begins when parts of a molecular cloud collapse under their own gravity, forming dense cores that eventually ignite nuclear fusion in their centers, giving birth to new stars. These stars can form in groups, creating open star clusters that gradually disperse over time as their stars drift apart. The distribution of stars, gas, and dust in the Milky Way is far from uniform. While the spiral arms are the most prominent features when viewed from above, the central bulge and the surrounding halo contain distinct populations of stars with different ages, compositions, and motions. The chemical composition of stars, known as their metallicity, varies throughout the galaxy and provides clues about their formation history. Stars in the galactic bulge and halo tend to have lower metallicities, suggesting that they formed early in the history of the Milky Way when fewer heavy elements were present. In contrast, stars in the thin disk, particularly those in the spiral arms, are generally richer in heavy elements, indicating that they formed later, after several generations of stars had produced and dispersed these elements into the interstellar medium. This ongoing cycle of star formation, evolution, and death is a critical part of the Milky Way's life cycle. When stars die, particularly in supernova explosions, they eject heavy elements into the interstellar medium, enriching it with the building blocks for future stars, planets, and even life itself. This process of chemical enrichment has led to the diversity of elements found in our solar system and on Earth. The study of the distribution and composition of stars in the Milky Way provides important insights into the processes of stellar and galactic evolution, helping astronomers piece together the history of our galaxy and its place in the universe. The Milky Way's structure and composition are complex and multifaceted, encompassing a wide range of stellar populations, interstellar material, and enigmatic dark matter. From the densely packed stars of the central bulge and the dynamic star-forming regions of the spiral arms to the ancient stars of the galactic halo and the invisible mass of dark matter, the Milky Way is a microcosm of the universe itself. Each component of the galaxy plays a crucial role in its overall dynamics and evolution, offering astronomers a wealth of information about the forces that shape galaxies and the cosmos. As our observational techniques continue to improve, we will undoubtedly uncover even more about the mysteries of our galactic home, deepening our understanding of the universe and our place within it. The Milky Way galaxy is a sprawling cosmic structure teeming with an astonishing variety of stars, each differing in size, temperature, brightness, and lifespan. The diversity of the Milky Way's stellar population is a reflection of the galaxy's rich history of star formation, evolution, and death over billions of years. From the massive, short-lived blue giants to the diminutive, long-lived red dwarfs, the stars that populate our galaxy offer insights into the life cycles of stars, the chemical enrichment of the interstellar medium, and the overall dynamics of the Milky Way. In addition to individual stars, the Milky Way also hosts various types of stellar remnants and star clusters, further enriching the tapestry of its stellar population. One of the most significant ways to categorize stars is by their spectral type, which is based on their surface temperature and the resulting color they emit. The hottest and most massive stars in the Milky Way are the blue giants, classified as O-type and B-type stars. These stars can reach surface temperatures of up to 30,000 to 50,000 Kelvin, making them extremely luminous and often appearing blue or bluish-white to the naked eye. Despite their impressive brightness and mass, blue giants are relatively rare because they burn through their nuclear fuel at a prodigious rate, with lifespans of only a few million years. These stars are usually found in regions of active star formation, particularly within the spiral arms of the Milky Way, where dense molecular clouds provide the necessary material for their birth. In contrast to the brief, intense lives of blue giants, the Milky Way is predominantly populated by red dwarfs, which are small, cool, and relatively faint stars classified as M-type stars. Red dwarfs have surface temperatures ranging from about 2,500 to 4,000 Kelvin, giving them a reddish hue. These stars are the most common type in the Milky Way, accounting for an estimated 70 to 80% of all stars in our galaxy. Unlike blue giants, red dwarfs are highly efficient in burning their hydrogen fuel, allowing them to live for tens of billions to even trillions of years. This incredible longevity means that many of the red dwarfs that formed early in the galaxy's history are still shining today. Due to their low luminosity, red dwarfs are difficult to detect from great distances, but their sheer abundance makes them a critical component of the Milky Way's stellar population. Yellow stars like our Sun, classified as G-type stars, fall in the middle of the stellar spectrum in terms of size, temperature, and lifespan. With surface temperatures around 5,500 to 6,000 Kelvin, these stars have a balanced combination of mass and luminosity, allowing them to sustain nuclear fusion in their cores for around 10 billion years. The Sun, for instance, is about 4.6 billion years old and is currently in the middle of its main sequence phase, during which it steadily converts hydrogen into helium. G-type stars are relatively common in the Milky Way and are often found in the galactic disk, where star formation is ongoing. In addition to the variety of stars on the main sequence, the Milky Way is home to more evolved stellar types, such as red giants and supergiants. As stars like the Sun exhaust their hydrogen fuel, they expand into red giants, increasing dramatically in size while their outer layers cool. Red giants, characterized by their reddish color and large radii, are in the late stages of their stellar evolution, burning helium in their cores after depleting their hydrogen. Some of the most massive stars evolve into even more luminous and larger red supergiants or blue supergiants, like Betelgeuse or Rigel, which are among the brightest stars visible from Earth. These supergiants are nearing the end of their lives and are destined to explode as supernovae, leaving behind neutron stars or black holes. As stars reach the end of their life cycles, they often leave behind stellar remnants, the cores of stars that have shed their outer layers or undergone catastrophic collapse. One of the most common types of stellar remnants in the Milky Way is the white dwarf, which is the final stage for stars with initial masses up to about 8 times that of the Sun. When a star like the Sun exhausts its nuclear fuel, it expels its outer layers in a beautiful display known as a planetary nebula, leaving behind a dense core composed mainly of carbon and oxygen. This remnant core becomes a white dwarf, which has no further nuclear fusion and gradually cools over billions of years. White dwarfs are incredibly dense. A teaspoon of white dwarf material would weigh several tons on Earth. They are often found in binary systems, where their interactions with a companion star can lead to phenomena like novae or even type IR supernovae if they accrete enough mass to exceed the Chandrasekhar limit. For stars much more massive than the Sun, the end of their life is marked by a supernova explosion, which results in the formation of either a neutron star or a black hole. Neutron stars are the remnants of stars that had masses between about 8 and 20 times that of the Sun. These stars collapse to a point where their protons and electrons combine to form neutrons, resulting in an incredibly dense object about the size of a city but with a mass greater than that of the Sun. Neutron stars can spin rapidly, emitting beams of radiation that we detect as pulsars. In the most extreme cases, when the original star was more than 20 times the mass of the Sun, the core collapse leads to the formation of a black hole, an object with gravity so strong that not even light can escape from it. The study of black holes, especially the supermassive black hole at the center of the Milky Way, Sagittarius A, is a key area of research in astrophysics, providing insights into the behavior of matter under extreme gravitational forces. Beyond individual stars, the Milky Way is also home to various star clusters, which are groups of stars that are gravitationally bound to each other. These clusters can be divided into two main types, open clusters and globular clusters. Open clusters, like the Pleiades, are relatively young, loosely bound groups of a few hundred to a few thousand stars. They are typically found in the spiral arms of the Milky Way, where active star formation occurs. Open clusters are rich in gas and dust and often contain many bright, young blue stars. Because they are not tightly bound, open clusters tend to disperse over time due to interactions with other stars and gravitational forces within the galactic disk. Globular clusters, on the other hand, are much older and more tightly bound collections of stars, often containing tens of thousands to millions of stars packed into a spherical shape. These clusters are usually found in the galactic halo, orbiting the Milky Way's core in highly elliptical orbits. Globular clusters, like Omega Centauri and Messier 13, are some of the oldest structures in the Milky Way, with ages of up to 12 billion years or more. The stars in these clusters are typically low in heavy elements, indicating that they formed in the early universe before the interstellar medium was enriched by multiple generations of star formation. The study of globular clusters provides valuable information about the early stages of the Milky Way's formation, and the conditions that prevailed in the early universe. One of the most interesting aspects of the Milky Way's stellar population is the prevalence of red dwarfs, which, despite their small size and low luminosity, dominate the galaxy in terms of numbers. Red dwarfs are the most stable stars, with lifespans that can exceed the current age of the universe. Their low mass means they burn their hydrogen fuel very slowly, and their stable conditions make them intriguing candidates for the search for exoplanets and potentially habitable worlds. Many of the exoplanets discovered in recent years orbit red dwarf stars, as these stars are relatively easier to observe due to their frequent flares and reduced brightness compared to Sun-like stars. The Milky Way's stellar population is not static, but is continuously evolving. New stars are born from the gas and dust in the interstellar medium, particularly within giant molecular clouds in the spiral arms. These regions, often referred to as stellar nurseries, give rise to star clusters that eventually disperse as their stars drift away. Over time, the galaxy's population of stars is gradually enriched with heavier elements produced in the cores of stars and ejected into the interstellar medium during supernovae. This process of chemical enrichment is fundamental to the evolution of the Milky Way, as it provides the raw materials needed for the formation of new stars, planets, and even life itself. In addition to the diversity of individual stars, the distribution of these stars across the Milky Way reveals important details about the galaxy's structure and history. The central bulge is dominated by older, metal-poor stars, while the galactic disk, particularly the thin disk, is rich with younger, metal-rich stars. The thick disk contains stars that are generally older and less metal-rich than those in the thin disk, suggesting that it may have formed during an earlier phase of the Milky Way's evolution, possibly through mergers with smaller galaxies. The halo is home to some of the oldest stars in the galaxy, often found in globular clusters, and these stars provide clues about the early history of the Milky Way and the universe. In summary, the Milky Way's stellar population is a rich and varied tapestry that spans a wide range of stellar types, ages, and evolutionary stages. From the massive blue giants that live fast and die young to the long-lived red dwarfs that quietly burn for trillions of years, the stars of the Milky Way reflect the complexity of the galaxy itself. The presence of stellar remnants like white dwarfs, neutron stars, and black holes adds to the diversity of the galaxy's inhabitants, each contributing to the ongoing cycle of star formation, evolution, and death. The study of star clusters, both open and globular, provides a window into the past, revealing the history of star formation in the Milky Way and the processes that have shaped the galaxy over billions of years. Understanding the stellar population of the Milky Way is not just about cataloging stars but is key to understanding the processes that govern the evolution of galaxies and the universe as a whole. The life cycle of stars is one of the most captivating and fundamental processes in the universe, driving the evolution of galaxies and contributing to the chemical enrichment of the cosmos. Stars are not eternal, they are born, evolve over time, and eventually die, leaving behind various remnants that continue to shape their surroundings. Understanding the life cycle of stars provides valuable insights into the formation of galaxies, the origins of elements, and the overall dynamics of the Milky Way. The journey of a star begins in dense regions of interstellar space known as molecular clouds, and it ends in a spectacular explosion or a gradual fading away, depending on the star's initial mass. The process of star formation begins in molecular clouds, which are vast, cold, and dense regions of gas and dust found throughout the Milky Way, particularly in its spiral arms. These clouds are often referred to as stellar nurseries because they provide the ideal conditions for the birth of new stars. Molecular clouds are primarily composed of hydrogen molecules, H2, along with traces of other gases and dust particles. The temperature within these clouds is typically very low, around 10 to 20 Kelvin, which allows gas molecules to move slowly and stick together, forming dense clumps. These clumps can become gravitationally unstable, especially when perturbed by external forces, such as supernova shock waves, the gravitational influence of nearby stars, or collisions with other clouds. When a region within a molecular cloud becomes dense enough, it begins to collapse under its own gravity, forming what is known as a protostar. During this collapse, the gravitational potential energy is converted into thermal energy, causing the core of the collapsing region to heat up. As the temperature and pressure increase, the protostar accumulates more material from the surrounding cloud, growing in mass. The process of accretion continues until the protostar reaches a point where nuclear fusion can ignite in its core. This marks the transition from a protostar to a main sequence star. The journey from molecular cloud to main sequence star can take several million years, during which the protostar may develop a surrounding disk of gas and dust, potentially giving rise to planetary systems. Once a star has ignited nuclear fusion in its core, it enters the main sequence phase, which is the longest and most stable period of a star's life cycle. During this phase, a star fuses hydrogen into helium in its core, releasing a tremendous amount of energy in the form of light and heat. This energy provides the outward pressure needed to counterbalance the inward pull of gravity, allowing the star to maintain a stable size and shape. The duration of the main sequence phase depends on the star's initial mass. Massive stars, which have much greater pressure and temperature in their cores, burn through their hydrogen fuel rapidly, often lasting only a few million years. In contrast, smaller stars like red dwarfs can remain on the main sequence for tens to hundreds of billions of years due to their lower core temperatures and slower fusion rates. Our Sun, a G-type main sequence star, is currently about 4.6 billion years old, and is expected to remain on the main sequence for another 5 billion years. During this time, it steadily converts hydrogen into helium, producing the energy that supports life on Earth. As a star ages, the hydrogen in its core gradually becomes depleted, and the balance between gravitational collapse and thermal pressure shifts. When the core runs out of hydrogen, the star's structure changes dramatically, marking the beginning of the end of its life cycle. The fate of a star after it leaves the main sequence depends primarily on its mass. For low to intermediate mass stars, like the Sun, the next stage is the red giant phase. As the hydrogen fuel in the core becomes exhausted, the core contracts and heats up, causing the outer layers to expand and cool. This expansion turns the star into a red giant, with a radius that can be several hundred times larger than its original size. In this phase, the star starts fusing helium into heavier elements like carbon and oxygen in a shell around the core. The increased energy output from these fusion reactions causes the outer layers to become unstable, and eventually, they are shed into space, forming a planetary nebula. The remaining core of the star, now devoid of its outer layers, becomes a white dwarf, a dense, hot remnant that gradually cools and dims over billions of years. For massive stars, those with at least 8 times the mass of the Sun, the life cycle is far more dramatic. After exhausting the hydrogen in their cores, these stars go through successive stages of fusion, creating heavier and heavier elements like carbon, neon, oxygen, and silicon. The process continues until the core is composed of iron, the most stable element in terms of nuclear fusion. Unlike lighter elements, iron does not release energy when fused, instead, it absorbs energy, leading to a catastrophic collapse of the star's core. The rapid core collapse triggers a supernova explosion, one of the most powerful and luminous events in the universe. Supernovae can outshine entire galaxies for a brief period and release more energy in a few seconds than our Sun will emit over its entire 10 billion year lifespan. The death of a massive star in a supernova has profound implications for the surrounding interstellar medium. The explosion disperses the star's outer layers into space, enriching the interstellar medium with heavy elements like carbon, oxygen, and iron, elements that are essential for the formation of planets and life. This process of chemical enrichment ensures that subsequent generations of stars are born with a richer supply of elements beyond hydrogen and helium. The shock waves from the supernova can also compress nearby molecular clouds, triggering the formation of new stars. In this way, supernovae act as both the death throes of massive stars and the catalysts for the birth of new ones, perpetuating the cycle of star formation in the Milky Way. Depending on the mass of the original star, the remnant left behind by a supernova can be either a neutron star or a black hole. Neutron stars are incredibly dense objects, composed almost entirely of neutrons, with a diameter of only about 20 kilometers but a mass greater than that of the Sun. They often rotate rapidly, emitting beams of radiation that can be detected as pulsars. Neutron stars represent one of the most extreme states of matter known to science, with densities so high that a teaspoon of neutron star material would weigh billions of tons. If the core remnant is massive enough, however, not even the degeneracy pressure of neutrons can halt the collapse, leading to the formation of a black hole. Black holes are regions of spacetime where gravity is so intense that not even light can escape, making them some of the most enigmatic objects in the universe. The impact of supernovae on the interstellar medium goes beyond merely enriching it with heavy elements. The energy released in a supernova can ionize vast regions of space, creating hot, expanding bubbles filled with high-energy particles. These supernova remnants, such as the Crab Nebula, can be observed as bright, glowing clouds of gas that continue to expand for thousands of years. The shock waves from supernovae also contribute to the turbulence in the interstellar medium, influencing the distribution of gas and dust within the galaxy. By stirring up the interstellar medium, supernovae play a key role in the dynamics of the Milky Way, affecting everything from star formation rates to the structure of spiral arms. Supernovae are not the only way stars can end their lives. In binary star systems, the interaction between two stars can lead to unique outcomes. For example, if one star in a binary system is a white dwarf, it can accrete material from its companion star. If the white dwarf accumulates enough mass to exceed the Chandrasekhar limit, about 1.4 times the mass of the Sun, it can trigger a thermonuclear explosion known as a Type Ia supernova. These supernovae are particularly important in astronomy because they serve as standard candles for measuring cosmic distances due to their consistent luminosity. Type Ia supernovae have been instrumental in the discovery of the accelerating expansion of the universe, which is attributed to dark energy. The final stage in the life cycle of stars is the contribution of their remnants to the galactic ecosystem. White dwarfs, which are the end state for low to intermediate mass stars, slowly cool and fade over billions of years, but they can still interact with their environment if they are part of a binary system. Neutron stars and black holes, on the other hand, have strong gravitational and magnetic fields that can influence their surroundings. For example, neutron stars that are also pulsars emit beams of electromagnetic radiation, which can be detected across vast distances, providing valuable information about the extreme states of matter. The life cycle of stars is a fundamental process that drives the evolution of the Milky Way and other galaxies. From the quiet birth of stars in molecular clouds to the violent deaths of massive stars in supernovae, each stage of a star's life has a profound impact on its surroundings. The formation of new stars, the creation of heavy elements, and the dispersal of these elements into the interstellar medium are all part of a continuous cycle that shapes the galaxy. Understanding the life cycle of stars is not only crucial for comprehending the nature of our galaxy but also for appreciating the origins of the elements that make up our planet and, ultimately, life itself. The study of stellar evolution thus provides a deeper understanding of our place in the cosmos, and the processes that have led to the rich diversity of stars and planets that we observe today. The Milky Way, our home galaxy, is a vast and complex structure, a cosmic island of stars, gas, dust, and dark matter. At its heart lies a supermassive black hole, surrounded by a disk of stars, nebulae, and planetary systems like our own solar system. Understanding the dynamics of the Milky Way, particularly its rotation and the forces at play within it, is crucial for gaining insight into both our local cosmic neighborhood and the broader universe. The rotation of the Milky Way is a phenomenon that has been studied extensively by astronomers and astrophysicists. The galaxy is not static but rather rotates as a whole, with stars and other celestial bodies orbiting the galactic center. This galactic rotation is an essential feature of the Milky Way's structure and behavior. It influences the distribution of stars, the movement of stellar clusters, and the dynamics of the interstellar medium. The way the Milky Way rotates can be seen as a grand cosmic dance, where individual stars and stellar systems follow orbital paths that are governed by the gravitational influence of the galaxy's mass, including its visible matter and the enigmatic dark matter. The Solar System, which resides in one of the outer arms of the Milky Way's spiral structure, is not stationary within the galaxy. It is in motion, orbiting the galactic center along with billions of other stars and stellar systems. Our solar system's journey through the Milky Way is a long and gradual process. It takes approximately 225 to 250 million years to complete one full orbit around the galactic center, a period known as a galactic year. This means that our Sun, along with its planetary companions, is constantly in motion, tracing an elliptical orbit around the center of the Milky Way. This motion is not uniform, but influenced by a variety of factors, including the distribution of mass within the galaxy and the gravitational interactions between stars and other celestial objects. Over the course of its journey through the galaxy, the solar system is affected by various forces that shape its trajectory. As the solar system orbits the galactic center, it moves through different regions of the Milky Way, encountering regions with varying densities of stars, gas clouds, and dark matter. These factors contribute to the way the solar system interacts with its galactic environment, influencing its position relative to other stars and its movement through the broader cosmic landscape. Mapping the Milky Way and understanding its complex structure is a monumental challenge. The Milky Way is vast, spanning over 100,000 light-years across, with the solar system positioned roughly 27,000 light-years from the galactic center. The sheer size and complexity of the galaxy make it difficult to obtain a comprehensive map. Astronomers have made significant strides in charting the Milky Way using a variety of techniques, including radio waves, infrared radiation, and other methods of observation. Radio telescopes, for example, have allowed scientists to map the distribution of hydrogen gas throughout the galaxy, providing valuable insights into its spiral structure. Infrared telescopes, on the other hand, help to penetrate the dense dust clouds that obscure our view in optical wavelengths, allowing us to see the central regions of the galaxy more clearly. However, despite these advances, mapping the Milky Way remains a difficult task, particularly when it comes to charting the distribution of dark matter and understanding the intricate details of its rotation and internal dynamics. Dark matter plays a crucial role in the stability of the Milky Way and in the overall structure of galaxies. Though it cannot be directly observed, its presence is inferred from its gravitational effects on visible matter. Dark matter makes up about 27% of the universe's mass-energy content, with ordinary matter, the kind that makes up stars, planets, and us, comprising only about 5%. The remaining 68% is made up of dark energy, a mysterious force that accelerates the expansion of the universe. Dark matter is thought to form a vast, unseen halo around galaxies, providing the extra mass needed to explain the observed gravitational effects that cannot be accounted for by visible matter alone. This dark matter halo is what helps to keep galaxies, including the Milky Way, from flying apart due to the rotational speeds of their outer stars. The presence of dark matter is essential for the galaxy's stability. Without it, the stars in the outer regions of the Milky Way would not have enough gravitational pull to remain bound to the galaxy, and the galaxy itself would begin to unravel. This dark matter, although invisible, acts like a cosmic glue, binding the galaxy together and ensuring that its stars and other celestial objects remain in their orbits. The interaction between dark matter and visible matter in the Milky Way is complex. As the galaxy rotates, the distribution of visible matter and dark matter is not uniform. While the visible matter is concentrated in the disk and bulge of the galaxy, dark matter forms a diffuse halo that extends far beyond the visible parts of the galaxy. The gravitational influence of this dark matter halo is what keeps the galaxy intact, preventing it from being torn apart by the centrifugal forces caused by its rotation. This interaction between visible and dark matter is one of the key factors that determine the overall structure and stability of galaxies, and it has significant implications for our understanding of the universe's evolution. The dynamics of the Milky Way are shaped by a combination of visible matter, dark matter, and gravitational forces. The rotation of the galaxy, the motion of the solar system, the challenges of mapping its structure, and the critical role of dark matter all contribute to the complexity and stability of the Milky Way. As astronomers continue to study the galaxy, they are gaining new insights into the forces that govern its behavior, leading to a deeper understanding of the universe as a whole. The study of planetary systems and exoplanets has revolutionized our understanding of the cosmos. As we expand our gaze beyond our own solar system, we encounter a vast array of planetary systems, each unique in its formation, composition, and potential for harboring life. The process of planetary formation, the variety of exoplanets discovered, and the search for Earth-like worlds all contribute to a deeper understanding of our place in the universe. This chapter explores the intricate dynamics of planetary systems, delving into the formation of planets and protoplanetary disks, the classification of exoplanets, the concept of the habitable zone, and the exciting discoveries of Earth-like planets. The formation of planets begins with the birth of stars. As a star forms from a cloud of gas and dust, a rotating disk of material, known as a protoplanetary disk, forms around it. This disk consists of gas, dust, and ice particles, which eventually collide and coalesce to form the building blocks of planets, known as planetesimals. Over time, these planetesimals collide and merge, gradually growing into protoplanets. The temperature, pressure, and chemical composition within the disk play crucial roles in determining the types of planets that will eventually form. Close to the star, where temperatures are higher, rocky planets like Earth are more likely to form, while farther out in the cooler regions, gas giants and icy bodies take shape. The process of planet formation is governed by the principles of gravitational accretion, where small particles gradually accumulate and stick together under the force of gravity. As the protoplanet grows, it begins to clear its orbital path of debris, eventually forming a fully fledged planet. The composition of these planets depends on the location within the protoplanetary disk. For example, in the inner regions of the disk, where temperatures are high, metals and silicates are more abundant, leading to the formation of terrestrial planets. In the outer regions, where it is colder, volatiles such as water, methane, and ammonia can freeze, leading to the formation of gas giants and icy moons. The discovery of exoplanets, or planets that orbit stars outside our solar system, has expanded our understanding of planetary systems. There are various types of exoplanets, each with unique characteristics and environments. One of the most notable categories of exoplanets are gas giants. These planets, similar to Jupiter and Saturn in our solar system, are composed primarily of hydrogen and helium, with deep atmospheres and possibly a solid core. Gas giants can be found in both close-in orbits around their stars and farther out, depending on their formation history. In some cases, gas giants can be located in so-called hot Jupiter's orbits, where they are positioned extremely close to their parent stars, leading to intense heat and unusual atmospheric conditions. Another important category of exoplanets is super-Earths. These planets are larger than Earth but smaller than the gas giants like Neptune and Uranus. Super-Earths can be rocky or gaseous and may possess conditions that are conducive to life, though much depends on their location and the type of star they orbit. Some super-Earths are located in the habitable zone of their stars, which is the region where liquid water could potentially exist on the planet's surface. Super-Earths have become a focus of exoplanet research due to their potential for harboring life and their relatively close proximity to Earth's size and composition. Hot Jupiters represent another fascinating class of exoplanets. These massive planets, often similar in size to Jupiter, orbit extremely close to their host stars, resulting in surface temperatures that can soar to several thousand degrees Celsius. The intense heat on hot Jupiters can cause their atmospheres to expand, leading to extreme weather patterns and unique atmospheric chemistry. These planets have been of particular interest to astronomers because their close orbits and extreme conditions provide an opportunity to study atmospheric properties in detail. In addition to the variety of exoplanets, another crucial concept in the search for extraterrestrial life is the habitable zone. The habitable zone, sometimes referred to as the Goldilocks zone, is the region around a star where conditions are just right for liquid water to exist on a planet's surface. Liquid water is considered a key ingredient for life as we know it, and planets within the habitable zone are prime targets in the search for extraterrestrial life. However, the habitable zone is not the only factor that determines a planet's potential to support life. The atmosphere, the presence of stable conditions, and the planet's composition also play vital roles in determining whether life could thrive on that world. The concept of the habitable zone is not static, it changes depending on the type of star. For instance, a red dwarf star, which is smaller and cooler than the Sun, has a habitable zone much closer to the star. Conversely, for hotter stars like blue giants, the habitable zone is farther out. As astronomers continue to discover exoplanets, the definition of the habitable zone is becoming more nuanced, accounting for a broader range of variables that could influence the potential for life. The search for Earth-like planets, those that share similar characteristics to our home world, has become one of the most exciting aspects of exoplanet research. Several factors make a planet Earth-like: it must be within the habitable zone of its star, have a stable atmosphere, and possess the right conditions for liquid water. As technology advances, the ability to detect and study Earth-like exoplanets has improved dramatically. Instruments like the Kepler Space Telescope and, more recently, the James Webb Space Telescope have revolutionized our ability to find and characterize planets in other star systems. One of the key methods for discovering Earth-like exoplanets is the transit method, which involves detecting the slight dimming of a star's light as a planet passes in front of it. This method allows astronomers to determine the size, orbit, and distance of an exoplanet from its star. In recent years, astronomers have found several candidates that may be Earth-like, particularly in terms of their size and location within the habitable zone. These discoveries are thrilling because they provide potential targets for the study of life beyond our solar system. While the discovery of Earth-like planets is a monumental achievement, it is important to note that finding a truly Earth-like world, one with a similar atmosphere, surface conditions, and potential for life, is still a work in progress. The study of exoplanet atmospheres is an emerging field, and scientists are now able to analyze the chemical composition of the atmospheres of some exoplanets. This data can help determine whether a planet has the right conditions for life, such as the presence of oxygen, methane, or carbon dioxide, which are all important indicators of biological processes. The study of planetary systems and exoplanets is rapidly evolving, offering a wealth of discoveries that deepen our understanding of the universe. From the formation of planets in protoplanetary disks to the classification of exoplanets into gas giants, super-Earths, and hot Jupiters, the diversity of worlds is vast. The concept of the habitable zone, and the search for Earth-like planets, continues to drive astronomical research. As technology advances and our methods for detecting and studying exoplanets improve, the dream of discovering another world capable of supporting life becomes ever more attainable. The Milky Way galaxy is home to countless phenomena that intrigue astronomers and astrophysicists alike. Beyond the familiar stars, planets, and nebulae that populate our cosmic neighborhood, there are a variety of more unusual and enigmatic objects and events that provide insight into the complexities of our galaxy. Rogue planets, brown dwarfs, planetary rings, and binary star systems are just a few of the unique celestial phenomena found in the Milky Way, each offering its own mysteries and challenges to our understanding of the universe. These phenomena not only broaden our knowledge of the types of celestial objects that exist but also play important roles in shaping the evolution of stars and planetary systems. The mystery of rogue planets is one of the most intriguing aspects of planetary science. Rogue planets are celestial bodies that do not orbit a star. Instead, they drift freely through the galaxy, unattached to any stellar system. This raises a significant question: how do planets end up wandering the galaxy without a star to orbit? One theory is that rogue planets are formed in the same way as regular planets within a protoplanetary disk around a young star. However, during the planet's formation, gravitational interactions with other planets or nearby objects could cause it to be ejected from its original star system, propelling it into interstellar space. Alternatively, rogue planets could form from the collapse of gas and dust clouds, much like brown dwarfs, but without the mass necessary to ignite nuclear fusion and become a star. Rogue planets are difficult to detect because they do not emit their own light, making them invisible in the vast darkness of space. However, astronomers have devised methods to detect them indirectly. For example, the gravitational influence of a rogue planet can cause the motion of nearby stars to waver slightly, a phenomenon known as gravitational microlensing. This effect can allow astronomers to spot a rogue planet when it passes in front of a distant star, briefly amplifying the star's light. While rogue planets are elusive, their discovery has important implications for our understanding of planetary formation and dynamics. These rogue worlds challenge the traditional notion of planetary systems being bound to a star and raise the possibility that there could be more rogue planets in the Milky Way than previously thought. Another fascinating celestial object that has captivated the attention of scientists is the brown dwarf. Brown dwarfs are often described as failed stars because they are too small to sustain the nuclear fusion process that powers stars like our Sun. However, brown dwarfs are not planets either, as they have a mass greater than that of Jupiter but insufficient mass to ignite fusion in their cores. The lower end of their mass range starts around 13 times the mass of Jupiter, and their upper mass limit is roughly 75 to 80 times that of Jupiter. While brown dwarfs lack the hydrogen fusion that occurs in stars, they can fuse deuterium and, at higher masses, lithium, which can provide a faint glow of energy. Brown dwarfs are typically very cold and faint, emitting mostly infrared radiation, which makes them challenging to observe using optical telescopes. However, infrared observations, such as those made by the Spitzer Space Telescope, have revealed the presence of many brown dwarfs in the Milky Way, often located in star-forming regions or orbiting larger stars. Brown dwarfs can form in similar ways to stars, from the collapse of gas and dust clouds, but they lack the critical mass required to start hydrogen fusion. Some brown dwarfs may have planets or moons orbiting them, and this has led to speculation about the possibility of life in these unusual environments, though the conditions would be very different from those on Earth. Despite their faintness and lack of true stellar characteristics, brown dwarfs are important objects for understanding the boundaries between stars and planets, and they may help bridge the gap in our understanding of stellar and planetary formation. Planetary rings are fascinating features found around many planets in the solar system, with Saturn's iconic rings being the most well-known example. These rings are made up of a combination of dust, ice particles, and small rocky debris, which orbit the planet in a thin, disk-like structure. The precise origins of planetary rings are complex and depend on a variety of factors, including tidal forces, the destruction of moons, and the dynamics of gravitational interactions. Understanding how these rings form and the processes that shape them offers valuable insights into the history of planetary systems and the forces at work in the universe. Planetary rings are composed of a wide range of particles that vary in size. These particles can range from tiny grains of dust, which are just a few micrometers in diameter, to large boulders several meters or even kilometers in size. The majority of ring material consists of water ice, which reflects sunlight and gives the rings their bright, reflective appearance. There are also smaller amounts of rock and dust, particularly in the inner rings. The composition of the rings can vary depending on the planet they surround and the specific conditions of the environment. The particles in planetary rings are not randomly scattered but tend to form distinct, concentric bands or rings that orbit the planet in a flat, disk-like formation. These rings are typically confined to a thin plane around the planet, with the thickness of the rings often being no more than a few kilometers. The particles within the rings follow individual orbits around the planet, and their interactions can lead to the formation of gaps and divisions between the rings. These gaps can be caused by gravitational interactions with moons or by the gravitational forces exerted by the planet itself. The particles in planetary rings are not static, and they can move and interact in various ways. Some particles may collide with one another, leading to the fragmentation of larger pieces into smaller debris. These collisions can also generate waves or ripples within the rings, which can propagate outward and affect the overall structure of the ring system. The gravitational influence of nearby moons can also play a role in shaping the rings, leading to the formation of gaps, waves, or ringlets within the broader ring system. The formation of planetary rings is believed to occur under specific conditions, most commonly when an object, such as a moon or comet, comes too close to the planet and is torn apart by the planet's tidal forces. These forces arise from the difference in gravitational pull experienced by the near and far sides of the object as it approaches the planet. If the object ventures within a certain distance from the planet, known as the Roche limit, the tidal forces become so strong that they can overcome the object's self-gravity and cause it to break apart. The fragments of the object then spread out and form a ring system around the planet. The Roche limit is a critical distance within which an object, whether a moon or a comet, can no longer maintain its integrity due to the tidal forces exerted by the planet. If the object is inside this limit, the difference in gravitational forces between the side of the object closest to the planet and the side farthest away is enough to disrupt the object and break it apart. The resulting debris then becomes part of the planetary ring system. The Roche limit varies depending on the size and density of the planet and the object. For example, Saturn's Roche limit for moons made of ice is about 147,000 kilometers, meaning that any moon that ventures within this distance could be torn apart and contribute to Saturn's rings. In addition to tidal forces, planetary rings can also form from the remnants of moons that were shattered by impacts or gravitational interactions. When a large object collides with a moon or when gravitational interactions between the planet and its moons cause the moon to be destabilized, the moon can be broken into smaller pieces. These fragments can then form a ring system, particularly if they remain within the Roche limit of the planet. In some cases, the debris from such events can accumulate over time and form dense, well-defined rings. Another theory of ring formation suggests that the material that forms the rings could have been present in the region around the planet from the beginning. During the early stages of the planet's formation, dust and ice particles may have gathered around the planet due to gravitational forces, and over time, these particles could have settled into a flat disk, forming the rings we observe today. However, this theory is less widely accepted than the idea of tidal disruption or the shattering of moons, as the exact mechanisms behind the formation of these primordial rings remain uncertain. The rings themselves can evolve over time. For example, collisions between particles within the rings can cause smaller particles to merge and grow into larger objects, which may eventually form moonlets, small moons that orbit within the rings or at their edges. These moonlets can exert gravitational forces on the surrounding ring particles, influencing the structure of the rings. Over millions of years, the ring system can change shape, lose material, or even disperse entirely, depending on the dynamics of the system and the forces acting upon it. One of the most striking features of planetary rings is their dynamic nature. For example, Saturn's rings are not static. They are constantly evolving due to the gravitational interactions between the particles within the rings and the nearby moons. Some moons, known as shepherd moons, can help maintain the structure of the rings by gravitationally interacting with the particles and preventing them from spreading out or dispersing. These moons can also create gaps in the rings by clearing out material through their gravitational influence, giving rise to the well-known divisions, such as the Cassini division, which separates the A and B rings of Saturn. In addition to shepherd moons, other forces, such as electromagnetic interactions, can play a role in shaping the rings. The charged particles within the rings can interact with the planet's magnetic field, leading to the formation of electric currents and complex interactions between the particles and the magnetic environment. These interactions can contribute to the overall structure of the rings and may influence the movement of particles within the system. Planetary rings are not a permanent feature of every planet. Over time, the material in the rings can be lost due to a variety of processes. For instance, ring particles can gradually spiral inward toward the planet due to gravitational drag or electromagnetic interactions, eventually being pulled into the planet's atmosphere or accreted onto its surface. This process can cause the rings to gradually dissipate and disappear over time. The lifespan of a ring system can vary greatly depending on the amount of material in the rings and the forces acting upon it. In some cases, planetary rings may persist for billions of years, while in other cases, they may only last for a relatively short period. The study of planetary rings offers important insights into the processes that shape planetary systems and the interactions between celestial bodies. These rings provide a snapshot of the dynamic and ever-changing nature of the universe, illustrating how gravitational forces, tidal interactions, and other physical processes can influence the structure and evolution of planets and their moons. Through continued observation and study, scientists hope to learn more about the conditions that lead to the formation of planetary rings, their long-term evolution, and their role in the broader context of planetary system dynamics. The rings of planets like Saturn serve as a reminder of the complex and beautiful forces that govern the cosmos, offering a window into the history and future of the universe itself. Planetary rings are not static, they are dynamic and constantly evolving. Over time, the particles that make up the rings can collide and merge, leading to the creation of new structures. The interactions between the particles also cause the rings to slowly change their shape and structure. In addition to tidal forces from the planet, other factors such as radiation pressure from the star, interactions with nearby moons, and the gravitational influence of other planets can all affect the shape and density of the rings. Planetary rings are also fascinating because they can serve as laboratories for studying the dynamics of disk systems, providing insights into the behavior of matter under the influence of gravity. The study of planetary rings can also shed light on the history and evolution of planets and their moons. For example, the rings of Saturn are thought to be relatively young, perhaps only a few 100 million years old, and they may have formed long after the planet itself was created. Other planets, such as Jupiter, Uranus, and Neptune, also possess ring systems, though they are much less prominent than Saturn's. The discovery of planetary rings around exoplanets has further expanded our understanding of ring systems, suggesting that they may be more common than previously thought. Studying the composition, structure, and evolution of planetary rings can help us understand the forces at play in planetary systems and provide clues about the conditions that existed in the early stages of planetary formation. The formation of binary star systems is another important topic in the study of celestial phenomena. Binary star systems, where two stars orbit a common center of mass, are quite common in the Milky Way. It is estimated that about half of all stars in our galaxy are part of binary or multiple star systems. Binary star systems can form in several ways. One possibility is that two stars form simultaneously from the same molecular cloud of gas and dust, with their mutual gravitational attraction causing them to orbit each other. Another possibility is that a single star captures a companion star, which then becomes gravitationally bound to it. Binary star systems come in a variety of configurations, depending on the masses and distances between the stars. In some cases, the stars are very close to each other, leading to the transfer of material between them, a phenomenon known as mass transfer. This can lead to the formation of accretion disks around one of the stars, and in some cases, this process can result in the formation of exotic objects like X-ray binaries or neutron stars. In other systems, the stars are farther apart, and their interactions are less intense. The gravitational influence of the two stars in a binary system can also affect the orbits of any planets or other objects in the system, causing them to be more unstable than those in single star systems. Binary star systems are important for astronomers because they provide a natural laboratory for studying stellar evolution. The interactions between the two stars, as well as their individual life cycles, can give insights into how stars evolve, how they exchange mass, and how their fates are intertwined. The study of binary star systems also plays a crucial role in measuring stellar masses, as the gravitational interactions between the two stars can be used to determine their individual masses with great accuracy. The Milky Way is home to a diverse array of unique celestial phenomena that deepen our understanding of the universe. Rogue planets challenge our conventional understanding of planetary systems. Brown dwarfs provide insight into the boundary between stars and planets, and planetary rings offer a window into the dynamic processes at play in planetary systems. The formation of binary star systems, one of the most common configurations of stars in the galaxy, offers a valuable tool for studying stellar evolution. Each of these phenomena contributes to our expanding knowledge of the cosmos and highlights the complexities and wonders of the Milky Way. The Milky Way, like all galaxies, is not an isolated entity but rather part of a dynamic and ever-evolving cosmic environment. Galaxies interact with one another in a variety of ways, with some even merging or colliding over billions of years. These interactions have profound effects on their structures, the formation of stars, and the overall evolution of galaxies. One of the most significant upcoming events in the history of the Milky Way is its collision with the Andromeda Galaxy, an event that will fundamentally reshape both galaxies. This chapter explores the implications of galactic interactions, particularly the Milky Way-Andromeda collision, the effects of galaxy mergers on structure and star formation, the role of gravitational interactions with nearby galaxies, and the impact of tidal forces on the Milky Way. The impending collision between the Milky Way and the Andromeda Galaxy, two of the largest galaxies in the local group, is one of the most anticipated events in the cosmic timeline. Andromeda, which is currently about 2.5 million light-years away from the Milky Way, is on a collision course with our galaxy. This collision is expected to occur in approximately 4.5 billion years. While this may sound catastrophic, astronomers believe that the actual collision between individual stars and planetary systems will be relatively rare due to the vast distances between stars. However, the gravitational interactions between the two galaxies will have profound effects on their structure, dynamics, and the formation of new stars. As the two galaxies approach one another, their gravitational fields will begin to interact. Initially, the Milky Way and Andromeda will experience tidal forces that will distort their shapes, creating long tails of stars and gas. The collision will trigger a massive wave of star formation, as the gas and dust within the galaxies are compressed by the gravitational forces. This process, known as a starburst, could lead to the formation of large clusters of stars. Over time, the two galaxies will pass through one another in a series of encounters, eventually merging to form a single, larger galaxy. This process will take place over several billion years, with the galaxies slowly coalescing into a single elliptical or lenticular galaxy, a transition that will profoundly alter the structure of both the Milky Way and Andromeda. During this collision, many of the stars in both galaxies will pass by one another without direct collisions. However, the gas and dust in both galaxies will experience much more dramatic interactions. The gravitational pull of each galaxy will compress the gas, triggering waves of star formation in both galaxies. Additionally, the central supermassive black holes at the cores of both galaxies are expected to eventually merge, releasing an enormous amount of energy in the form of gravitational waves. This merger will lead to the creation of a new supermassive black hole at the center of the newly formed galaxy. The entire event will reshape the galactic structure, leaving behind a new galaxy with a much different morphology than either the Milky Way or Andromeda currently has. Galaxy mergers, like the one between the Milky Way and Andromeda, play a significant role in the evolution of galaxies. The merging of two galaxies can lead to a complete transformation of their structure. For example, a spiral galaxy like the Milky Way could be transformed into an elliptical or lenticular galaxy after a merger, as the gravitational forces between the merging galaxies disrupt their spiral structures. This transformation occurs because the gravitational interactions cause the stars and gas in both galaxies to be redistributed in random orientations. The result is a more spherical or ellipsoidal shape, with stars spread out more evenly across the galaxy. In the case of the Milky Way and Andromeda, their spiral shapes are expected to be lost during the merger, with the final result being a large elliptical galaxy. Galaxy mergers also significantly affect star formation. When two galaxies collide, the gas within them is compressed by the gravitational forces, leading to an increase in star formation. This phenomenon is known as a starburst, and it occurs when large clouds of gas are compressed into regions of high density, triggering the rapid formation of new stars. The starburst phase is often short-lived, as the gas is quickly consumed in the formation of stars. In some cases, galaxy mergers can lead to an even more intense starburst phase, where large clusters of stars are formed at an accelerated rate. However, after the merger, star formation tends to slow down as the gas is depleted, and the galaxy transitions to a more quiescent state. In the case of the Milky Way and Andromeda, this starburst phase will likely be a key feature of the merger, resulting in the creation of vast numbers of new stars. The role of gravitational interactions between galaxies extends beyond just mergers. Even galaxies that do not collide can influence each other through their gravitational fields. These interactions can result in a variety of outcomes, from minor distortions in the shape of a galaxy to significant changes in its structure. For example, gravitational interactions between galaxies can lead to the transfer of gas and stars from one galaxy to another. In some cases, this can result in one galaxy being stripped of its gas, leading to a decrease in star formation. In other cases, galaxies can exchange stars or even form tidal tails, long streams of stars and gas that are pulled out of one galaxy by the gravitational pull of a nearby galaxy. One of the most notable examples of gravitational interactions in the local group is the relationship between the Milky Way and the Large Magellanic Cloud, LMC, a satellite galaxy that orbits our galaxy. The gravitational pull of the Milky Way has caused the LMC to distort, and the two galaxies are currently in the process of exchanging gas and stars. This interaction is expected to eventually lead to the merger of the LMC with the Milky Way, although this event is still billions of years away. Gravitational interactions between galaxies can also lead to the formation of galaxy clusters, where multiple galaxies are bound together by their mutual gravitational attraction. These clusters can contain hundreds or even thousands of galaxies, all interacting with one another in complex ways. Tidal forces are another crucial factor in galactic interactions, particularly during galaxy mergers. Tidal forces arise from the gravitational pull that one galaxy exerts on another, and they can have dramatic effects on the galaxies involved. When two galaxies pass close to one another, their gravitational fields stretch and distort each other, creating tidal forces that can tear apart stars, gas clouds, and even entire galaxies. These tidal forces are responsible for the formation of tidal tails, which are long streams of stars and gas that are pulled out of galaxies during close encounters. The tidal forces during the Milky Way-Andromeda collision will be particularly strong, and they will reshape the structure of both galaxies, triggering waves of star formation and potentially leading to the creation of new structures, such as tidal dwarf galaxies. In the Milky Way, tidal forces from the Andromeda Galaxy will be felt long before the two galaxies physically collide. These forces will gradually stretch the Milky Way, causing it to lose stars and gas, and will influence the motion of the stars within the galaxy. The tidal forces will also affect the outer regions of the galaxy, leading to the stripping of stars and the formation of long tidal streams. The impact of these tidal forces on the Milky Way will be profound, but the actual collision between the two galaxies will be an even more significant event in the galaxy's evolution. The Milky Way's future collision with the Andromeda Galaxy is one of the most significant events in the galaxy's history. The merger will have profound effects on the structure of both galaxies, including the transformation of their spiral forms into an elliptical galaxy, the creation of new stars in a starburst phase, and the formation of a new supermassive black hole at the galactic center. In addition to galaxy mergers, gravitational interactions with nearby galaxies play an important role in shaping the structure of galaxies and influencing star formation. Tidal forces, in particular, have the ability to reshape entire galaxies, triggering the formation of tidal tails and impacting the motion of stars. As the Milky Way and Andromeda galaxies move closer to one another, these forces will shape the future of both galaxies, leading to a new era of galactic evolution. The cosmos is filled with a wide range of exotic objects and forces that challenge our understanding of physics and astronomy. From magnetas, the most extreme type of neutron star, to the mysterious influence of dark matter, the universe is home to some of the most fascinating and perplexing phenomena. Gamma-ray bursts and supermassive black holes also represent some of the most energetic and impactful events in the universe. These objects and forces not only provide crucial insights into the fundamental workings of the universe but also play key roles in the evolution of galaxies and the cosmos as a whole. This chapter will explore these exotic objects in detail, shedding light on their nature, behavior, and the profound effects they have on the universe. Magnetas, a subclass of neutron stars, are among the most extreme objects in the universe. Neutron stars themselves are the remnants of massive stars that have exploded in supernovae, leaving behind a dense, compact core. These stars have incredibly strong gravitational fields, with masses between 1.4 and 2 times that of the Sun, but their radii are only about 10 to 20 kilometers, making them one of the densest objects known. However, magnetas take this extreme nature to a whole new level. A magnetar is a neutron star with an exceptionally strong magnetic field, typically 1,000 times stronger than the typical neutron star magnetic fields, which are already powerful beyond imagination. The magnetic field of a magnetar can be up to 100 trillion Gauss, which is about 1 billion times stronger than the magnetic field of Earth. This intense magnetic field has dramatic effects on the magnetar's surroundings. The extreme magnetic forces can cause the star to emit bursts of high-energy radiation, particularly in the form of X-rays and gamma rays. Magnetas are highly unstable, and their magnetic fields can cause the star's surface to crack, a phenomenon known as starquakes. These starquakes can release enormous amounts of energy, leading to bursts of radiation that are detectable across vast distances. Magnetas also emit soft gamma-ray repeaters, SGRs, and anomalous X-ray pulsars, AXPs, which are the primary types of magnetas observed. These bursts of energy are so powerful that they can affect the space around the magnetar, distorting time and space due to their immense gravitational and electromagnetic forces. The study of magnetas helps scientists probe the behavior of matter under extreme conditions, including high-density states, strong magnetic fields, and intense gravitational forces. Magnetas are thought to be the result of the collapse of a massive star's core during a supernova explosion, although the exact process behind the formation of their ultra-strong magnetic fields is still not fully understood. The discovery and observation of magnetas offer a unique opportunity to study the interactions between gravity, magnetism, and nuclear physics in extreme environments. Gamma-ray bursts, GRBs, are one of the most energetic and mysterious phenomena in the universe. These bursts of gamma radiation, the most energetic form of light, can release more energy in a few seconds than the Sun will emit in its entire 10 billion-year lifetime. Gamma-ray bursts are typically observed in distant galaxies and are thought to be associated with the death of massive stars. They occur in 2 primary types: long-duration GRBs and short-duration GRBs. Long-duration GRBs are thought to be caused by the collapse of a massive star into a black hole, which results in the formation of a relativistic jet of particles that emits gamma radiation as it travels outward. These bursts can last anywhere from a few seconds to several minutes. Short-duration GRBs, on the other hand, are believed to be the result of the collision of 2 compact objects, such as 2 neutron stars or a neutron star and a black hole. The merger of these objects creates a highly energetic explosion, producing a burst of gamma rays. While long-duration GRBs are more common, short-duration GRBs are just as energetic, and their precise mechanisms are still a subject of intense study. Both types of GRBs release massive amounts of energy in a very short period of time, and their after effects can be observed across vast distances. The cosmic implications of gamma-ray bursts are profound. They are thought to be one of the primary sources of the heavy elements found in the universe, as the explosive nature of GRBs can trigger the synthesis of elements like gold and platinum. GRBs also provide insight into the behavior of matter and energy under extreme conditions, as well as the processes that occur when compact objects like black holes and neutron stars merge. The study of GRBs has significantly advanced our understanding of stellar evolution, particularly in the context of massive stars and the formation of black holes. In addition to their role in stellar evolution, gamma-ray bursts are also significant for the study of cosmology. The high energy emitted by GRBs allows astronomers to probe the distant universe, as the bursts can be observed from galaxies billions of light-years away. The study of GRBs provides valuable information about the early universe, as these bursts are often associated with the formation of new stars in distant galaxies. By studying the light curves and spectra of GRBs, astronomers can learn more about the conditions and processes that existed in the universe when it was still young. Dark matter, though invisible and undetectable by traditional means, is thought to account for roughly 85% of the total mass in the universe. Despite its elusive nature, dark matter plays a critical role in the structure and dynamics of galaxies, galaxy clusters, and the universe as a whole. While we cannot directly observe dark matter, its presence is inferred through its gravitational effects on visible matter. For example, the rotation curves of galaxies, plots of the speed of stars as a function of their distance from the galactic center, show that stars in the outer regions of galaxies are moving much faster than would be expected based solely on the visible matter in the galaxy. This discrepancy suggests the presence of an invisible form of mass, dark matter, that is exerting additional gravitational pull. Dark matter also plays a crucial role in the formation and evolution of galaxies. During the early stages of the universe, dark matter clumped together due to gravitational attraction, forming vast halos around galaxies. These dark matter halos provided the gravitational foundation for the formation of galaxies, ensuring that galaxies had the necessary mass to form and evolve. Dark matter also affects the dynamics of galaxy clusters, where the gravitational influence of dark matter is responsible for holding the clusters together. Without dark matter, galaxies and galaxy clusters would not have the gravitational support needed to maintain their structure and cohesion. Despite being the dominant form of matter in the universe, the precise nature of dark matter remains one of the most important unsolved mysteries in physics and astronomy. Several candidates have been proposed for dark matter, including weakly interacting massive particles, WIMPs, axions, and sterile neutrinos, but no definitive detection has been made as of yet. The study of dark matter is a key area of research in astrophysics and particle physics, as understanding its properties could provide insights into the fundamental nature of the universe and the forces that govern its behavior. Supermassive black holes are another exotic object that plays a significant role in the evolution of galaxies. These black holes, which are typically millions to billions of times more massive than the Sun, reside at the centers of most large galaxies, including the Milky Way. Supermassive black holes are thought to have formed early in the history of the universe, potentially as a result of the collapse of massive gas clouds or the merging of smaller black holes. They are found at the cores of many galaxies, and their immense gravitational pull influences the dynamics of the galaxy as a whole. The presence of a supermassive black hole at the center of a galaxy has significant implications for the galaxy's evolution. Supermassive black holes are often surrounded by accretion disks, which consist of gas and dust that spiral in toward the black hole. As this material falls in, it heats up and emits radiation, including X-rays and gamma rays. This process, known as active galactic nuclei, AGN, can result in the emission of massive amounts of energy, which can have a profound effect on the surrounding galaxy. The radiation from an AGN can heat the interstellar medium, suppressing star formation and potentially halting the growth of the galaxy. Additionally, the powerful jets of material emitted by some supermassive black holes can interact with the surrounding gas, driving outflows that can affect the growth and evolution of the galaxy. Supermassive black holes are also thought to play a key role in the formation and growth of galaxies. The interaction between a black hole and its surrounding material can lead to the formation of large-scale structures, such as galaxy halos and supermassive black hole mergers. The energy emitted by supermassive black holes can also trigger the formation of new stars, although the relationship between black holes and star formation is complex and not fully understood. Ultimately, supermassive black holes are central to our understanding of galaxy evolution, as they influence the growth, structure, and behavior of galaxies throughout the universe. Exotic objects like magnetas, gamma-ray bursts, dark matter, and supermassive black holes represent some of the most fascinating and complex phenomena in the universe. These objects not only challenge our understanding of the fundamental forces that govern the cosmos but also play critical roles in the formation, evolution, and behavior of galaxies. The study of these objects offers valuable insights into the nature of the universe, the processes that shape it, and the forces that drive its evolution. As astronomers continue to observe and study these exotic objects, they will undoubtedly reveal even more mysteries about the cosmos and the fundamental forces that govern it. The exploration of the universe has been one of humanity's most enduring pursuits, driven by our desire to understand the cosmos and our place within it. Over the past century, technological advancements have revolutionized our ability to observe distant stars, galaxies, and other cosmic phenomena. Modern astronomy has developed a range of sophisticated tools and techniques that allow scientists to explore the universe in ways that were once unimaginable. Space telescopes like Gaia and Kepler, for instance, have provided invaluable data, expanding our knowledge of everything from the formation of stars to the search for Earth-like planets in distant star systems. However, despite these remarkable advances, many profound questions about the universe remain unanswered, particularly concerning the formation of galaxies and the fundamental forces that shape the cosmos. Looking ahead, new frontiers in cosmic exploration are poised to push the boundaries of human knowledge even further, offering the potential to unlock some of the deepest mysteries of the universe. Astronomical observation is a multifaceted science, utilizing various techniques to study the universe across the entire electromagnetic spectrum. Visible light is just one of many wavelengths through which we observe the universe, and other wavelengths, such as radio waves, X-rays, and gamma rays, provide critical insights into different aspects of celestial objects and phenomena. The first major breakthrough in astronomical observation came with the invention of the telescope, which allowed astronomers to study distant objects with unprecedented clarity. Over time, telescopes have become much more sophisticated, now able to capture images and spectra across various wavelengths, and at extremely high resolutions. One of the most fundamental techniques in modern astronomy is photometry, which involves measuring the brightness of celestial objects at different wavelengths of light. This technique provides information about the composition, temperature, distance, and motion of stars, galaxies, and other astronomical bodies. Spectroscopy, another vital technique, involves the analysis of light through a prism or diffraction grating, breaking it up into its component wavelengths. By studying the resulting spectra, astronomers can determine the chemical composition, temperature, and motion of celestial objects. Both photometry and spectroscopy are often conducted using ground-based telescopes and space telescopes, which offer complementary perspectives of the universe. Ground-based observatories, while valuable, have limitations due to the Earth's atmosphere, which can distort incoming light and block certain wavelengths. This is where space telescopes come into play. By positioning telescopes in space, astronomers can avoid atmospheric interference and observe the universe with greater clarity. Space telescopes, such as Gaia and Kepler, have revolutionized our understanding of the cosmos, providing an unparalleled view of the stars, planets, and galaxies. Gaia, a space observatory launched by the European Space Agency in 2013, is one of the most significant space telescopes in operation today. Its primary mission is to create a detailed 3D map of the Milky Way galaxy, measuring the positions, distances, and motions of over 1 billion stars. The accuracy and precision of Gaia's measurements are unprecedented, allowing astronomers to study the structure and dynamics of the Milky Way in incredible detail. In addition to its mapping mission, Gaia has also contributed to the discovery of exoplanets, observed stellar evolution, and provided insight into the distribution of dark matter in our galaxy. Gaia's ability to measure the motion of stars across the sky has helped us understand the gravitational interactions that shape the galaxy and allowed astronomers to map the Milky Way's spiral arms, providing new insights into the formation and evolution of our galaxy. Kepler, another groundbreaking space telescope, was launched by NASA in 2009 with the goal of finding exoplanets, planets orbiting stars outside our solar system. By monitoring the brightness of over 150,000 stars, Kepler detected small variations in brightness caused by planets transiting across the face of their stars. This technique, known as the transit method, has proven to be incredibly effective in identifying exoplanets, and Kepler's discoveries have vastly expanded our understanding of planetary systems. Kepler has revealed thousands of exoplanets, many of which are located in the habitable zone of their parent stars, where conditions may be suitable for liquid water to exist. Kepler's legacy has provided critical insights into the prevalence of planets in the universe and the potential for life beyond Earth. Despite the successes of Gaia and Kepler, many fundamental questions about the universe remain unanswered. One of the most significant unsolved mysteries in astronomy is the formation of galaxies. Galaxies are the fundamental building blocks of the universe, yet the processes that govern their formation and evolution are still not fully understood. Current models of galaxy formation suggest that galaxies formed from the cooling and collapse of gas in the early universe, eventually forming stars, gas clouds, and dark matter halos that coalesced into the galaxies we see today. However, many details of this process remain unclear. For instance, it is still uncertain how galaxies acquire their shapes, whether they are influenced by the initial conditions of the universe, by interactions with other galaxies, or by the presence of supermassive black holes at their centers. In addition, the role of dark matter in galaxy formation is still a major area of research. Dark matter, which accounts for about 85% of the mass in the universe, is invisible to current observational techniques, yet its gravitational effects are felt throughout the cosmos. It is thought that dark matter plays a crucial role in the formation of galaxies, providing the gravitational pull necessary for galaxies to form and remain stable. However, the exact nature of dark matter remains elusive, and its interactions with normal matter are still a subject of intense study. Understanding how dark matter influences galaxy formation could shed light on the evolution of the cosmos and the forces that govern it. Another major question in astronomy is the nature of supermassive black holes and their role in galactic evolution. Supermassive black holes are found at the centers of most large galaxies, and their formation is thought to be linked to the evolution of the galaxies themselves. Some theories suggest that supermassive black holes may form through the accretion of gas and dust in the early universe, while others propose that they could have originated from the merger of smaller black holes. The relationship between black holes and galaxy evolution is complex, and scientists are still working to understand how these enigmatic objects influence the structure and behavior of galaxies over time. Recent discoveries, such as the detection of gravitational waves from black hole mergers, have provided new insights into these objects, but much remains to be learned. As we look to the future of cosmic exploration, the prospects for discovering new and exciting phenomena are boundless. Several upcoming missions and technological advancements promise to expand our understanding of the universe. The James Webb Space Telescope, JWST, set to launch in 2021, is one of the most anticipated space observatories of the next decade. JWST is designed to observe the universe in the infrared part of the spectrum, allowing it to study objects that are too faint or distant to be observed in visible light. With its powerful instruments, JWST will help scientists probe the early universe, study the formation of stars and galaxies, and search for signs of life on exoplanets. In addition to JWST, new ground-based observatories are being developed, such as the Extremely Large Telescope, ELT, being built by the European Southern Observatory. Once completed, the ELT will be the largest optical telescope in the world, with a primary mirror that is 39 meters in diameter. The ELT will be able to observe the universe with unprecedented detail, providing insights into the formation of planets, the search for life beyond Earth, and the study of supermassive black holes. Another promising avenue of exploration is the search for extraterrestrial life. As our understanding of exoplanets grows, scientists are increasingly focused on identifying planets in the habitable zone, regions around stars where liquid water could exist. Missions like NASA's TESS, Transiting Exoplanet Survey satellite, are working to identify these planets, and upcoming telescopes like the LUVOIR, Large Ultraviolet Optical Infrared Surveyor, mission may allow scientists to study the atmospheres of Earth-like exoplanets in more detail, searching for signs of life. The future of cosmic exploration also holds the potential for breakthroughs in understanding the fundamental nature of the universe. The study of dark energy, which is driving the accelerated expansion of the universe, and dark matter, which constitutes much of the universe's mass, could lead to new insights into the underlying forces that govern the cosmos. Additionally, upcoming missions and experiments may provide answers to questions about the nature of black holes, the origins of the universe, and the ultimate fate of the cosmos. The exploration of the universe is an ongoing journey that continues to reveal new and exciting mysteries. Space telescopes like Gaia and Kepler have already made remarkable contributions to our understanding of the cosmos, and upcoming missions like the James Webb Space Telescope and the Extremely Large Telescope promise to expand our knowledge even further. Despite these advancements, many profound questions remain unanswered, particularly regarding the formation of galaxies, the role of dark matter, and the nature of supermassive black holes. As we look to the future, the prospects for cosmic exploration are boundless, offering the potential to unlock some of the deepest mysteries of the universe. Through continued observation, research, and technological innovation, we are poised to make exciting discoveries that will shape our understanding of the cosmos for generations to come. We'd love to hear your thoughts in the comments below. If you found this topic fascinating, don't forget to like, share, and subscribe for more engaging content. Thank you for journeying with us here on Frontiers of Infinity.